Hello, welcome to the third lecture of the NPTEL course Fundamentals of Composite and Cellular Materials. In this lecture, we will cover the classes of materials and the basics of material property charts. In the previous lectures, we have already covered the fundamentals of hybrid materials. We defined what are the hybrid materials. We classified the hybrid materials into two broad groups like composites and cellular materials, and in the last lecture we also learned that how materials design process from a material selection aspect should be done in a systematic manner to actually exploit all the benefits of the available materials. And you will see today that if this material selection aspect and the materials for designing is done in a systematic manner, then hybrid materials can actually provide properties which are actually not attainable by bulk materials. The main portions covered in today's lecture will be the basic description of the various classes of bulk materials and their properties, and I will give you the fundamental aspects of material property charts and how and where the hybrid materials are typically located. Please keep in mind that a more detailed definition, not definition, a more detailed description of the material property charts will be covered in the upcoming lectures. The basic keywords that will be covered in this lecture are classes of materials, metals, ceramics and glasses, polymers and elastomers, hybrids and material property charts. So, what we will do today, because it is a fundamental course, so we will now kind of describe the basic fundamental properties of each of these material classes briefly, and that will actually help us to put the hybrid materials like composites and cellular solids, which are actually the focus of this course, into perspective. As you can see, this pentagon on the right hand side, this actually shows the basic classes of monolithic or classical monolithic materials, and these basic material classes are classified into ceramics, glasses, elastomers, polymers and metals. Now, what about the ceramics? So, ceramics, as you know, there are many examples of ceramics like aluminum oxide Al2O3, then silicon carbide SiC, boron carbide B4C, silicon nitride Si3N4, and there are also elemental ceramics like carbon in the form of graphite or diamond. Now, as you know that ceramics, I mean all these specific classes like ceramics, metals, polymers, they actually differ in the terms in terms of the interatomic bonding. In ceramics, the bonding is typically either ionic bonding or covalent bonding. It is never a completely ionic bonding, it is almost always a mixed bonding, and the amount of ionic nature actually depends upon the difference between the electronegativities of the constituent elements. Now, as we know that ceramics, because of the ionic and covalent bonding, these bonds are extremely strong, and this very high bond strength actually renders the ceramic to have the highest Young's modulus. The highest Young's modulus of any bulk material is actually attained in diamond, which is even more than 1 terapascal, that is 1000 gigapascal. To compare metals like steels, which is pretty high Young's modulus in case of metals, they are typically having a value of around 200 gigapascal. And for aluminum, we obtain a value much lower, around 70 gigapascal. The high bond strength of the ionic and covalent bond also provides the ceramic with very high melting point. Like diamond, it can have a melting point more than 4000 degrees Celsius. There are also other ceramics like ultra high temperature ceramics like zirconium diboride, or for example like your hafnium diboride. These materials typically have melting point more than 3000 degrees Celsius. So, these are actually the basic advantages of ceramics. Ceramics also possess lower density than metals. This is because of the fact that in a typical ceramic, it is combined or kind of constituted of typically one metal and a non-metal, like aluminum oxide is constituted of aluminum and oxygen. There are also ceramics where both elements are kind of non-metals, like boron carbide, where boron and carbon. And also ceramics have lower packing factor than metals, and these actually provide ceramics with relatively low density. Like one ceramic boron carbide has a density of only 2.54 gram per cc, which is extremely low. But at the flip side, ceramics are extremely brittle with low resistance to crack propagation because of the low fracture toughness. Why are ceramics brittle? Now, because of the strong ionic and covalent bond, ceramics typically have extremely high lattice resistance, and that is why although dislocations are present, they are actually not mobile, and that is the reason that when the ceramics are loaded, they actually undergo fracture before plastic deformation. Also, ceramic properties are very much dependent upon the type of loading that they are subjected to. Because ceramics possess extremely low fracture toughness, and even a small crack can actually propagate in a catastrophic manner, ceramics are actually very low or very poor in tensile loading. That means, if a ceramic sample is loaded under tension, it is almost always that a sample breaks even after the test starts. But if the same sample is loaded under compression, because under compression the crack is not opening, it is closing, and that is why ceramics typically possess significantly higher strength in compression than in tension. This is typically exploited for many design applications like the bricks that are used for our houses and where we stay. Ceramics also possess good, they are also generally good insulators. This is also because in ceramics there are no free electrons. There is only because of whatever conduction takes place, this is because of the lattice vibration, and because of that most of the ceramics are good insulators. Ceramics are also resistant to corrosion, and because of their extremely high melting point, ceramics can retain their strength at elevated temperatures. So, all these things actually make ceramics very good, an ideal material for many applications, but one big problem is that the only one or two aspects which kind of kills all the good properties of ceramics are basically, one is its extremely high brittleness and its low fracture toughness. That means, when a hybrid is actually developed for a ceramic material or a ceramic containing material, the aim is to actually increase the fracture toughness, because ceramics already possess high strength and stiffness. After ceramics, the other most commonly used material in our day-to-day applications are the metals. Now, metals, as you know, they possess a metallic bond. In a metallic bond, as you know, it is not localized. That means, there are metallic ions, and all the valence electrons, they actually kind of donated in a pool, and then they are actually mobile, and that is the reason that metallic bond is not localized, and this non-localized metallic bond is actually responsible for many of the properties of metals. Also, the bond strength of the metallic bond is lower than the ionic bond and the covalent bond, and that is why the metals typically possess lower Young's modulus and lower melting point than ceramics. However, there are some metals like, for example, tungsten, which has extremely high melting point, like more than 3400 degrees Celsius, and also there are also other metals like silver. Now, apart from this high medium high melting point and Young's modulus, one of the drawbacks for metals in lightweight applications is its high density. Now, the high density of the metals is because of the relatively high atomic mass of the elements and also the relatively high packing factor. So, if you see, like densities of metals like iron has a density of almost 8. There are definitely light metals like magnesium or aluminum, but there are also metals like gold, silver, tungsten, which are extremely heavy, or lead, for example, which is used, the high density of lead is kind of exploited for the radiation shielding. So, if we compare the density of metals with ceramics, generally ceramics almost always possess a lower density than the metals. That means, adding ceramics to metals in a hybrid material can actually lower the density of the material, which is actually good, and because ceramics also possess higher higher strength and stiffness, I mean having a hybrid with metal and ceramic can actually provide you with a material having a high value of stiffness and a low value of density, that means a high specific stiffness. Apart from that, metals also have an extremely positive attribute, that is they are soft and ductile in pure condition. This is because of the presence of numerous dislocations and the non-localized metallic bond, which does not hinder the movement of the dislocations, and that is why metals are easily compliant and they are tough, and that actually gives the metals the extremely good formability, which is extremely important for many applications. Like we see around us all the structural applications, these are all possible because metals allow to be formed into various shapes because of its high ductility and malleability. Apart from that, metals also provide the possibility to kind of optimize or enhance the properties like typically strength, hardness, etc. by alloying. Typical example is the steels. I mean, as you know, steel is an alloy of iron and carbon. So, as such, iron does not have good properties, but if carbon is added into suitable amount and also provided sufficient amount or suitable heat treatment, then one can actually develop thousands of different kinds of steels having different strength, ductility and hardness properties, and this is again extremely important for many applications of metals. Also aluminum alloys like precipitation hardening or cold working, these can actually provide a wide range of strength. Because of the availability of free electrons, which are actually kind of charge carriers, metals are good conductors of heat and electricity. That is why metals typically possess a high conductivity, like copper or silver, they have extremely high conductivity, but as there are more defects are actually kind of added into metals, then the conductivity actually goes down. But metals, one drawback, typically some of the metals are prone to corrosion and they may also undergo fatigue under cycling loading conditions. So, if we now, I mean we have just discussed two different classifications, ceramics and metals. So, we can see that there are many properties where ceramics and metals actually complement each other, like density for example, where ceramics have low density, metals have high density. Like the modulus for example, ceramics have high modulus, metals possess low modulus. Like for example the toughness, ceramics have low toughness, metals have high toughness. So, that means the combination of a ceramic and metal to fabricate a hybrid material actually can open up a huge horizon of materials where we can use different combinations in different dimensions, in different forms, in different volume fractions. Apart from ceramics and metals, there are also other materials which are also important like glasses. So, glasses, as you know, they are non-crystalline solids, they are actually solidified without crystallization, and glasses are also many properties are like the ceramics, like they lack plastic deformation, they are also pretty hard and brittle, and they are also resistant to corrosion. Elastomers is another very important class of materials in our day to day life, like the rubbers that we use. So, elastomers basically they are a kind of polymers where the individual polymer chains they are actually cross linked with some kind of a van der Waals bond or kind of weak bond, and when a elastomer is actually kind of tense, kind of loaded in tension, then this cross link regions actually provide some resistance to kind of displacement of the chains, and that actually provides elastomers with good elastic properties. Finally, polymers. So, polymers are covalent solids. So, polymers again, as you know, so many of the materials around our surrounding us are actually polymers. So, polymers, so carbon-carbon chains are the fundamental building block of a polymer, and the name polymer actually comes from the fact that you have the monomers, and if these monomers are actually polymerized, then a polymer is actually formed. And again, polymers have very low modulus because they have the intermolecular bond is covalent bond, which is a strong bond, but the interchain bond is weak van der Waals bond, and because of that polymers generally possess low modulus and also low melting point. but because of the fact that polymers possess a low density, because the constituent elements like carbon, hydrogen, nitrogen, oxygen, these are very low density elements, and because of that polymers typically have very low density. So, actually the modern polymer engineering which has come up a very large way, and even in aerospace, for example, in the modern aircrafts, significant amount of materials are either based on polymers or polymer based composites, because polymers actually provide low temperature fabrication because of their low melting point. That means at those applications where melting point or high temperature is not a limiting factor, polymers are ideal material because they also provide extremely high ductility, damage tolerance, and if you compare the specific strength of polymers with metals, in many cases polymers can actually outperform the metals. Also polymers are resistant to corrosion and they can easily be shaped and formed. So, these are now the individual classes of the basic classical materials which we have or which we have had from the beginning of our civilization. Now, as I have mentioned several times, the scope of this particular course is to provide or to develop an understanding of the hybrid materials. What are hybrid materials? According to this diagram by Ashby, a hybrid material is actually a combination of any of the material classes, like you can combine a ceramic and the polymer to obtain a ceramic fiber reinforced polymer of CFRP, you can combine a ceramic and the metal like a metal matrix composite, and you can also combine a ceramic and a ceramic to obtain a ceramic matrix composite. So, these and also you can actually add upon one more phase, as I discussed in the first lecture. You can actually also add significant amount of voids in the material to actually obtain cellular solid like cellular ceramic, cellular metal or cellular polymer. So, now I discussed about various kinds of hybrid materials. So, now as we are slowly, I mean this slide or this content of this slide, I think I discussed in very brief detail in the first lecture. But now because we are slowly moving into our actual topic of hybrid material development for many applications, I think it is also important that again the various structures possible with the common hybrid materials are again discussed. So, here the image number A or the schematic of the A actually shows you a particle reinforced composite. That means the particles here, the matrix, that means the white phase is a typical ductile material like it can be a metal, and the particles, like if you want to increase the strength or stiffness at lower density, one can actually add ceramic particles into a metallic matrix to obtain a particle reinforced composite. One can also obtain, like in a ceramic reinforced ceramic body, also other ceramic particles that will enhance the toughness of the material. In case of polymer, they are typically called not particles, they are typically called as filler materials. Image number B is actually shows you, again it is a composite material, but it is called unidirectional fiber reinforced composite. So, you can see the basic difference between 1 and 2 is that in 1 or in A, the particles are kind of distributed in a homogeneous manner along all directions, and this actually renders the particle reinforced composite a isotropic property. Whereas, for continuous fiber reinforced polymers or composites, the fibers are all along one direction, that means along the vertical direction, and that will actually provide the material with extremely high anisotropy. That means the properties along the fiber direction are good, and the properties along the transverse direction, that means the two horizontal direction, can even be poorer than the matrix. Image number E actually shows you the short fiber reinforced composites, where the continuous fibers, because they are highly anisotropic, they are actually chopped into small length and then they are distributed in a random fashion to actually give you more isotropy. Definitely the properties along the fiber direction are lower, but because you also win upon the anisotropy, which is a very big plus. Image number F actually shows you a laminate composite. This is again one direction, one design with the continuous fibers, where each laminate can have different orientation of the fibers, and that will again provide you less amount of anisotropy. Image number C is so called interpenetrating composites, like here both the ceramic phase and the metallic phase both are continuous. That means you first fabricate a porous ceramic body, and within that you infiltrate a metal to actually have a very high ceramic content, much higher than the particle reinforced composites, but also providing you better properties like lower expansion coefficient and all those things. Image number D shows you functionally graded composites. So, these are so called FGM materials, like if you want to have a material with different properties along different lengths, that means if you want a material with a high hardness at the top surface and a low toughness at the bottom, you can actually develop a material with high ceramic content at the surface and low ceramic content or low or high metal at the core, and that will actually provide you a graded composite. These are all examples of composite structures. Then image number G actually shows you a closed cell foam, where again the red region or the red walls, these you can see the cell walls and the cell faces, and image number H, where all the cell faces have been replaced with kind of window, open window, you get an open cell foam. So, in this slide, so basically if we just discuss about whatever material properties we have discussed so far, in this slide we see that whatever discussion we made, they actually follow the discussion. Like if we see, this is a single axis plot of only Young's modulus as a function of different material classes. So, you can see as discussed already, ceramics, and this plot is in log fashion. So, you can see the ceramics typically have the highest Young's modulus because of the strong covalent and ionic bonds. Metals follow suit because metals have metallic bond. Composites lie in between, they can be between for MMCs or ceramic or metal matrix composites, they can be between the ceramics and the metals, and for ceramic reinforced polymers, they can be between your polymer and the ceramic phase. And only polymers, like the light blue region, they have extremely low modulus because of the weak van der Waals bond. Now, this was one way of kind of classifying the materials, but as I already mentioned, there is no one parameter designing in materials. Like as an engineer, we have to always optimize between different parameters, and more often than less, we have to combine different parameters. So, the next slide actually shows you one example of how to combine different material properties and how actually the hybrid materials actually broaden the horizon of our bulk materials. So, you can see in this plot, so now this plot again has some typical characteristics. This is a typical plot of Young's modulus along y axis and density along x axis, and similar plots have been developed. These are called so-called Ashby plots after the name of Mike Ashby, who actually invented this kind of plots. Now, in these Ashby plots, you can see there are also other property parameters like strength over modulus, like your strength over density, fracture toughness over modulus. So, some of these plots will be discussed in the next lecture. Now, what we see over here is that the first point that actually draws our attention is that the axes of the two plots both are actually logarithmic. These are not linear axes. Why? Because you can see that the density, both density and Young's modulus actually vary over a wide range. Like density varies from over almost 3 orders of magnitude or more than 3 orders of magnitude, whereas for Young's modulus it is almost 7 to 8 orders of magnitude. That means, if we simply plot linear plots or kind of the linear, then it will be enormous and we cannot fit all the materials in one single plot, and that is why the axes of both the plots or both the axes of these plots are actually made in the logarithmic scale. The second important factor is that you see here that there are individual balloons. That means, there is one balloon which is for natural materials, one balloon for the ceramics, one balloon for the metals, one balloon for the elastomers, and basically these balloons actually restrict the materials because of fundamental physical reasons which we already discussed about the bonding and all those things. Not all the regions can be filled up with only these simple classical materials. That means, if you see that these balloons of the large materials, they actually kind of restricted or they cover only some specific regions within a plot. And if you see the next slide, what is done now, actually if we now plot all the individual materials, see all the metals, they actually form small bubbles, they actually cover kind of, they are encircled by the balloons. That means, all metallic materials fall within the metallic balloon, all ceramics fall within the ceramic balloon, and so on. Now, here is again the beauty of the hybrid materials, as you can see by the two dotted lines being shown, two dotted red circles being shown over here, or ellipses actually. So, you can see that hybrid materials actually provide you regions in the material property chart which are actually not filled up by any of the bulk materials. That means, what I mentioned at the very beginning of this lecture or this course, that one of the most important aims of hybrid material development is to create a space filler in the material property chart as per our requirement. So, this chart actually shows that we can, with the hybrid materials, we can attain the properties or domains which are not possible with any other bulk material. So, this brings us to the conclusion of this lecture. So, in this lecture we discussed the primary property attributes of different material classes like metals, ceramic, glasses, polymers, elastomers, and we also discussed that how the concept of hybrid material development should be utilized or exploited to actually choose the best properties from different materials. To reiterate again, if you want to develop a hybrid of metals and ceramics, metals typically have high density, high ductility, ceramics typically have low density, low fracture toughness but high stiffness. That means, combining a metal and ceramic in the appropriate design or appropriate dimensions or appropriate shapes can actually provide you a material with good combination of density, of low density, high stiffness and reasonably high fracture toughness. And also we discussed about the basic idea of a material property chart in the form of Young's modulus over density, and in the next in the next slide or in the next lecture we will actually cover some more material property charts like modulus density, strength over density, specific modulus over specific strength, and then we will move on to the concept of material indices and again define that how the material indices play a very important role in the hybrid material design. The topics of this lecture have been taken from the book Material Selection in Mechanical Design by Mike Ashby. Thank you very much.